So let's pick back up where we left off, talking about the wave equation. And just a bit of review. So if you remember from last time, we derived D'Alembert's formula for the wave equation. So the general initial value problem for the wave equation is the second time derivative of u is equal to c squared second space derivative of u on r and t greater than 0. And we have an initial condition u of x at 0 equals phi, and u t of x at 0 equals psi, okay? And these are defined on R, and phi is C2, and psi is C1, so that we have a classical solution. And D'Alembert's formula tells us that if we have an initial value problem like this that satisfies those constraints, then the solution is going to look like the sum of the initial position propagated to the right and to the left, plus a scaling of the integral over the initial velocity. Okay, so that's going to propagate as well from any initial disturbance in the velocity. So we worked out why that is the formula for the solution. It has to do with the fact that these two characteristics are strongly indicative of what happens to the initial conditions in the wave equation. So if we have this initial value problem, which we call dagger, and we want to say something about continuous dependence, then we can use D'Alembert's formula in order to show that any solution, as we change the initial data, will continuously depend on that initial data. Okay, so suppose that UK is a solution to that initial value problem with initial position phi k and initial velocity psi k, for k equals 1 and 2. So we have two different initial value problems, but their initial data are presumably not far from each other. We want to show that when the difference between this initial data is small, in other words, less than some small parameter epsilon, then the difference between the solutions should be small, okay, for any t, okay, greater than 0. How are we going to do this? Okay, well, we'll just use D'Alembert's formula, okay? And so essentially we can just compute this using D'Alembert's formula and show that we can bound it based on our knowledge of the initial condition, okay? So let's compute just u1 of xt minus u2 of xt. This is equal to a half of phi 1 minus phi 2 of x plus ct, plus a half of phi 1 minus phi 2 evaluated at x minus ct. plus 1 over 2c integral from x minus ct up to x plus ct of psi 1 minus psi 2 evaluated at y d1. Okay. So we can bound this, okay, by passing in the absolute values that we have. So first of all, we can upper bound this part by just taking absolute values of phi 1 and phi 2 of x plus ct, phi 1 minus phi 2 of x minus ct, okay? And then integrating the absolute value of psi 1 minus psi 2 evaluated at y dy. Okay, so how does this hold? Well, this basically follows from the triangle inequality, okay? And continuity, which allows us to say, well, the absolute value of an integral is bounded by the integral, the absolute value of that function, okay? So when we put all those things together, right, we know that this is small, this difference is small, right? Because the infinity norm, or the sort of maximum difference of this is small. This is small as well. And also the difference of this is small throughout. So what we have then is that u1 minus u2, so evaluated at xt, is bounded from above by epsilon over 2, okay? That's because this part we can just say is bounded from above by epsilon. This part here is bounded from above by epsilon. This part on the interior here is bounded from above by epsilon, okay? So we have epsilon over 2 plus epsilon over 2, okay, plus 1 over 2c to ct epsilon, because the limits of this go from x minus ct up to x plus ct, so that difference will be 2ct. And so this is just equal to 1 plus t epsilon, okay? So basically, for any finite t, as long, we can always, if we make this epsilon as small as we like, then this quantity will be small as long as t stays finite. But obviously, as t goes up to infinity, right, we can always take t to infinity, okay? So the point is, this is true if phi 1 minus phi 2 and psi 1 minus psi 2 are uniformly small, okay? This implies that u1 minus u2 is small at each x in R for t greater than 2, okay? But of course, we must take t to be finite, okay? Basically because of the t epsilon term, okay, as I said before. And that's, of course, unless we can put a bound on this integral, the integral from minus infinity to infinity of phi psi 1 y minus psi 2 y dy is less than epsilon, okay? And so this would be like the one norm of psi. So another way to ensure continuous dependence would be to say, well, if I make the one norm of this small and the infinity norm of the difference between phi 1 and phi 2 small, then even for an unbounded value of t, I'm going to have a continuous dependence. Okay, so that's continuous dependence.